Today we're going to begin our discussion on geometric sequences. I'd like to look at an example that's not technically a sequence, but it does follow the rule of a geometric situation. This is Moore's Law. I don't know if you've heard of this or not. It's a pretty amazing observation of transistors and circuits, integrated circuits. And Gordon Moore was co-founder, obviously as it says here, the Intel and Fairchild Semiconductor. It's 1965. He described doubling every year of the transistors in integrated circuits. It turns out that it doubles every 2 years based on data since 1965. That's still an amazing fact. If we look at a graph here of transistors as we look over the years, all the way back, if we look down here at this area where we're looking at about 4,000 transistors, and then when we get up here, an amazing amount. You can see the y-axis here. This looks like a linear relationship, but if you kind of look at the transistor count here, obviously the y-axis is not going up in a linear fashion. This is an exponential function, which ties directly to geometric functions. This is what we call the doubling function, so our ratio is 2. If this continues, we are going to have some amazing computers in not too long. So let's look at how that plays out in terms of a geometric sequence. Just a nice little example to look at that. If we look at thinking about the first year recorded there, 4,000 transistors, and then doubling every 2 years. So we'd have 8,000 2 years after the first, and then 16,000, and then 32,000. Again, amazing fact, and his law has held true over the years, even into the 2000s. So one of the things that you'll have to do with geometric sequences is to find an expression for the common ratio. So right here, this a of n and a of n minus 1 are kind of generally thinking about that, so I'll look at that with you, and then we'll look at some actual numbers here and how that plays out. So let's focus on the a of n and the a of n minus 1 expressions. So remember, when we're looking at a sequence, we could have a of n is just any term in the sequence. And remember that before that term is a of n minus 1, and of course after that term would be a of n plus 1. So this problem here is asking you to find a common ratio expression given a of n and a of n minus 1. So to find the ratio for any geometric sequence, we take some term, like a of n, and we divide by the previous term, a of n minus 1. And that'll give us our ratio. We could also think about it as the next set in this sequence here. Let me circle these here. We could also take a of n plus 1 and divide by the previous term. So there's a of n plus 1, and divide by the previous term, which in this case is a of n. Okay, so this is an expression that indicates the ratio given a couple terms there. Okay, now let's use some numbers, a little bit easier to grasp there, in case you didn't catch that. So let's look at how it plays out with numbers. So for example, if I look at these two terms here, 8,000 and 4,000, we can see that we're multiplying by 2 every time. So times 2 and times 2. And later in this video, we'll look at an example that's a little bit tougher to see. So all you do is you take some term, like 8,000, and divide by the previous term, and that's going to give you your ratio. So our ratio equals some term divided by the previous term. And in this case, we used a2 divided by a1. And of course, what we get is 2. So there's our ratio of 2. We could have also used some other terms in the sequence. If it's geometric, it'll hold true every time. If we take some term like 16,000 and divide by the previous term, 8,000, we can see that's also equal to 2. So that's how we find our ratio for a geometric sequence. Okay, next let's look at how we determine whether a sequence is arithmetic, geometric, or neither. In this case, we're going to start with our first sequence here, and we can easily see by just looking at the sequence that it's going up by 2. So we're adding 2 every time, so we call that a common difference in this case. So yes, this one is arithmetic. And remember, arithmetic is either going to be a plus or a minus. So we're adding or subtracting for arithmetic sequences. Okay, next let's look at this one here in blue. And we can see here that we're multiplying by 3 every time. So this is geometric. I'll just indicate that with geo. And our ratio is 3. So we've identified that it's geometric, and we've also talked about its ratio. Now the next example is a little bit tougher to see, so I'm going to do a little bit of work down here just to show you. When I first look at the sequence, it's hard to tell whether it's being added, subtracted, or multiply and divide. In this case, it's going to be a geometric sequence, and I'll show why that's true. So we're going to indicate that this is geometric. And again, when you look at something tough like this, you don't know. So let's follow our rule of finding the ratio. So we'll take the second term, which is -4, and divide by 6, and that's going to give us -2/3. Okay, we can also, let's confirm that it works, because just because we get a ratio doesn't mean that it's a geometric sequence. That ratio has to hold true for each consecutive set of terms. So our next example is we'll take A3 divided by A2 just to check it. And in this case, A3 is 8/3. Okay, and we're going to divide that by A2, which is -4. Now, I'm not going to show the calculations here. You can do it on a calculator, however you do fractions. What we end up with is -2/3. So that's our comma ratio. So ratio equals -2/3. So that is geometric. We've just shown that. Now this last example down here does not hold true for either geometric or arithmetic. So we'll say neither. There is no number that adds or subtracts or multiplies or divides to get that sequence. Now it's still a sequence, but it means it just follows another rule. Okay, the next piece I want to look at is how do we write an explicit formula for a geometric sequence? And this turns out to be pretty easy for the most part. Once we find the ratio and the first term, it's a pretty easy formula to work with. So we're going to just say a of n. Remember that acts like our y. And we're going to say a1, just like we start our arithmetic sequence. But in this case, remember it's multiplication. So I'm going to indicate that with parentheses and put my ratio there, and then raise it to the n minus 1. Now remember, again, this r is our ratio, and this n in this case acts like our x. So if you want to make a connection to functions rather than sequences, that's what that looks like. All right, so this is our general formula. I'm going to circle that. That's our general formula for explicit formula for geometric sequences. One thing that I want to just make sure you understand too, we've already gone over recursive formulas for arithmetic sequences. And I got an extra I in there. Take that out. Recursive formulas there. A little trouble spelling there. Okay, so what we're going to do here is A1. So we're just going to indicate our sequence A1. So we'll say A1 equals something. And then we'll say A of n equals the previous term times a ratio. So just like that. So if we go back to our transistor example, we can write our recursive formula like this. We started with 4,000 transistors, and our ratio was 2. So we put a 2 there. Okay, so this would be recursive. And then this one over here is our explicit formula. And if we were going to plug stuff in for our transistor example, it would look like this. So remember, A1 is also 4,000. And then over here, our ratio is 2. The helpful part of explicit formulas is that we can find any term in the sequence. So if we were looking at year 30 or something like that, now we would have to come up with a rule there. Now we'd have to kind of work on that n a little bit, because remember it doubles every 2 years and not every 1 year. So this is not a steadfast rule for that example, but it does a good example of where you plug stuff in for recursive versus explicit. Okay, the last thing I want to do in this video is go over a couple examples of how you find indicated terms for a geometric sequence, given some information. So we're going to look at this example here. We'll look at just example A on the slide, and then I'll clear it out so that we can look at the second example. Remember, our explicit formula, which tells us any term in the sequence at any time, is going to look like this. We have A of n equals A1 times the ratio raised to the n minus 1. And so let's go ahead and write our explicit formula, and then we'll plug in what we need to know. So we have an A1 of -2, and then our ratio is going to be 3, and we're going to raise that to the 8 minus 1. Okay, so now we got to be careful with our order operations here. We're going to make sure that we do our exponent first. So A, and we're trying to find A8, so we'll put an 8 there. We have -2, and then we're doing 3 to the 7th. And 3 to the 7th is 2187. So A8 equals -2 times 2187. And what we get is 4374. So A8 is 4374. And that's going to be a negative because we have a negative 2 there. So negative 4,374 is our eighth term. Okay, our second example here, we're going to look at example B. Example B here. This time we're trying to find A12. So it's going to work the same way. Remember, we're going to start with our general formula. A of n equals A1 times the ratio raised to the n minus 1. In this case, we're trying to find A12. Our first term is 1,024. Again, I recommend parentheses around the ratio there. So we have negative 1/2. And we're raising it to the 12 minus 1. And it just as a efficiency thing, we can kind of cut to the chase and say 12 minus 1 is 11. Okay, so again, do your order operations first. We have negative 0.5 raised to the 11th. Okay, and that's going to give us, let's see, so we still have 1,024 here. When we do negative 1/2 raised to the 11th, we get negative 1 over 2,048. Okay, we're going to multiply that by 1,024. Okay, and so A12 equals negative 1/2. And that concludes our discussion on geometric sequences. Hopefully that helped. I'll see you in the next video.